Hi everyone! Last time we saw what an integral was. This time we're going to explore some properties of integrals. So let's just jump right in. It is important to remember the conceptual understanding of an integral, that it's an area under a curve. Remembering this will help us to figure out some of these properties even if we happen to forget them. We're going to cover 7 properties today. It's likely that you'll forget 1 or 2 of them, but that's okay. We'll brush up, and as long as you retain that understanding that an integral is an area under a curve, you can figure out these properties for yourselves, even in tough, pressured situations. So let's just jump right in here. If we have the integral from a to b of f of x, for all of these properties, we're going to assume that every function is integrable. We can integrate it. And we're going to also assume that it's integrable at least on the intervals a to b or b to c or whatever intervals we're using, but in general we'll just say it's integrable everywhere. This is an area under a curve from a to b. This is an area under a curve from b to a. Because the interval is exactly the same, these should be the same areas. In this particular area, you're moving from left to right. We're moving to the right. In this particular area, you're moving from right to left. You're moving to the left. That means when we move to the left, we always say that it's negative. So these 2 areas should be exactly the same, but this one is the negative of this one. So to make it the same, we'll have to introduce the second negative. And negative times negative will give us back the positive. That's our first property. Second property, if we're integrating f from a to a, we'll just get 0. We start at a, we end at a, the width of our interval is 0, so the area there has to be 0 as well. If we're integrating from a to b, some constant times f, remember constant just does a vertical stretch. So this is saying stretch out the function, then find its area. This will be the same thing as if we find the area and then stretch it afterwards. So this should be the same thing as first finding the area and then stretching it. And our fourth property here, if we have the integral from a to b of f plus g, that's going to be the same as finding the area under f and adding it to the area under g. And the same thing is true with subtraction, so I'm just going to make these pluses or minuses. These are our first 4 properties here. Take a minute, make sure you've internalized them and written them down, and then I'll erase them. The next 3 properties are still intuitive, but perhaps slightly less so. If we have the integral from a to b of f, and we're adding it to the integral from b to c of f, well, here we're finding the area from a to b and we're stopping at b. Here we're finding the area from b to c, and we're stopping at c, but we're starting at b. So that means we've gone till b, stopped, started again exactly at b, and kept going all the way to c. That means what I've done is I've found 2 areas that are right next to each other, that are literally touching each other. This is just the area from a all the way to c of f. Similarly, I could use this property in reverse. If I had an area from a to c, I could split it apart to a to b plus b to c, which occasionally will be quite helpful when shapes get a little weird or wonky, or if I have a piecewise function, things like that. So this is good to know both ways. Great. Next, let's say I have the integral from a to b of f, and I want to approximate this. I don't know what it is, but I want to approximate it. Okay. So this is an area. The width of the interval is b to a. So I know that if I picked the smallest possible f value, the minimum f value, and I made a rectangle right there, one rectangle, and a RAM with just one as my number of partitions, the area of that rectangle, since it has the minimum f value and the width is the whole interval, the area of that rectangle has to be less than or equal to this particular integral. This is less than or equal to, b minus a, the width of the interval, times the minimum f value, which I'll call f min. And similarly, the integral itself is less than or equal to b minus a, the width of the interval, times f max. This will be particularly helpful when we get a function and we're like, shoot, I really don't know how to integrate this function. Let me just try to ballpark approximate, give myself a good idea of what's happening here. And last but not least, if f of x is greater than or equal to g of x on all of ab, then the integral of f of x on AB is greater than or equal to the integral from a to b of g. And this might seem like common sense, right? If one function's higher than another function, of course the area under it's going to be bigger than the area under the other function. This is surprisingly useful for us, especially when we get functions that we have no idea how to integrate. We can compare them to functions that we do know how to integrate and give ourselves a ballpark answer here. In particular, and don't worry too much about this for now, we can say, oh, let's say there's an infinite area under g of x, and I was able to integrate it. Well, then that means the area under f of x also has to be infinite because f is always bigger than g. This is related to end behavior models that we saw back in the fall. We have one super ugly function, we don't know what to do with it, so what we do instead is we take a super nice function that's very closely related, and we integrate that one instead. Just like in the past, we found the end behavior instead. And those are our 7 properties. So, now that we have those properties, let's dive in and try some practice problems out. The first couple are going to be kind of abstract. We're just going to play around for a bit, and then we'll get to some more concrete ones with actual function formulas. So, first, I'm going to give you 3 facts. The integral from -1 to 2 of f of x is 3. The integral from 2 to 3 of g of x is 7. Oops, I forgot my dx. And the integral from 3 to 2 of f of x is 2. Question 1. What is the integral from -1 to 3 of f of x? And question 2. What is the integral from 2 to 3 of f of x plus g of x dx? Maybe you want to pause the video here, try these out for yourselves, see if your answers match the answers that I'm about to give. But if you'd just like to follow along, that's fine too. If I want to find the integral from -1 to 3 of f of x, I know the integral from -1 to 2. If I also knew from 2 to 3, then I would have all the way from -1 to 3. But I don't know the integral from 2 to 3. I do know the integral from 3 to 2, though. So we remember one of our properties says that if you change the order of the bounds, if you flipped this, instead of being from 3 to 2, you made it from 2 to 3. Reversing the order you go just makes this negative instead of positive, or positive instead of negative, or keeps it at 0. The only difference is the minus sign, right? Here I'm going from right to left, and I got 2. So if I'm going from left to right, I should get the opposite of 2, which is -2. Great. If from -1 to 2 I'm at 3, and then from 2 to 3 I'm at -2, I can add these two things together to get me from -1 all the way to 3. So that answer should be 1. To do question 2 here, I want the integral of f plus g. Well, I don't know f or g, so I'll use my property that this integral is really the integral of f plus the integral of g. I do know the integral of f on 2 to 3, I just found that out, that's -2. I also know the integral of g from 2 to 3, that's 7. So this answer should be -2 plus 7, which is just 5. So there's a couple of abstract problems for you. And now we'll give it a little bit more meat by giving some actual functions to you and seeing how they go. So, let's do the following. Let's say I have a function here, and that function is h of x, and that's equal to the square root of 2 minus sine x. And I want to approximate the integral from 0 to pi over 2 of h. Okay, well, to do this, what I'll do is I'll use one of the properties that I saw earlier, which is this particular area has to be sandwiched between the minimum value of h times the width of the interval and the maximum value of h times the width of the interval. We recognize that the width of our interval from 0 to pi over 2 is just pi over 2. What's the minimum value of h? Well, the minimum value of h happens when this particular expression, 2 minus x, is as small as possible. That happens when sine is as large as possible, which happens at pi over 2 when sine is 1. So that's just the square root of 2 minus 1, which is the square root of 1, which is 1. So h of x is at least pi over 2, which is like, 1.5, 1.6. And that's fine. And the maximum value of h times the width of the interval should be our upper bound here. So pi over 2, again, is the width of the interval. The maximum value of h happens when sine is as small as it can be. On this particular interval, that happens at 0. Sine of 0 is 0. 2 minus 0 is 2. So this is times square root of 2. And pi over 2 times root 2, that's around 2. That's around 2. So we have this nice value of our integral sandwiched somewhere between about 1.5 and about 2. So we have a pretty good idea of where that comes from. This particular function would be really, really hideous to have to do a RAM estimation with. And so this estimation is going to be good enough until we learn some techniques of integration that can help us out with it. Okay. This particular problem here, we looked at the minimum value of h and the maximum value of h. The thing is, just like when we looked at LRAM and RRAM, one is going to be quite the underestimate, one is going to be quite the overestimate. Wouldn't it be nice to have something somewhere in the middle? So let's try to find the average value of a given function. We remember that an average is just the total amount of stuff divided by the number of things we have. For instance, if you had 3 test grades of 90, 80, and 70, the average would be adding 90, 80, and 70 and dividing by 3 since you had 3 tests. So this is what we'll do here. The average value of f on a particular interval, let's say on AB, is going to be the total area, which is the integral from a to b of f, divided by the length of the interval here, which is b minus a. So that's actually going to be 1 over b minus a. Okay. This is exactly the same average that we calculate always. We take the total, we divide by how many things we have, and we get out our average. So total area divided by length of interval should be the average value of the function. So, for instance, if f of x is something like 3x squared plus 2, and I wanted to know on 0 to 2, what's the average value of my function? Well, I can just set it up. So let's set this up here. Average f should be equal to 1 over b minus a, which is 1/2. And I'll multiply that by the integral from 0 to 2 of 3x squared plus 2 dx. And I'll just use my nifty calculator, which you may recall has that fn int right here. If I go to math and I select number 9, it'll give me my integral. I want to go from 0 to 2. I want my function to be 3x squared plus 2. I want it to be with respect to x. I can hit enter, and there you have it. I'll have my value, 12. Great. So that integral is equal to 12, and then 1/2 times 12 gives me 6. So the average value of this function on this interval is 6. Does that make any sense to us? Well, if we plugged in 0 to this function, we'd get 2. If we plugged in 2 to this function, we'd get 14. So it should probably be somewhere between 2 and 14. And 6 is, so that's really good. If we got some number that wasn't between the minimum and maximum, that would be really bad. It wouldn't be the average, right? And so you're probably sitting there being like, okay, so I have the average. Cool, now I can figure it out. But why is this interesting or helpful or useful at all? Well, you might recall another word for average in math class is the word mean, and you might recall that when you hear the word mean, you instantly think of a theorem that we saw earlier in the year called the mean value theorem, or MVT for short. The mean value theorem, when we looked at it with regular functions, it just said, oh, okay, if you are taking derivatives, there's some special point c where the derivative at c is equal to the average rate of change. And we actually have a very, very similar theorem for integrals. So this is the MVT for integrals. There is some, so there is a c in the interval AB such that f of c is equal to the average value of f, which again is 1 over b minus a times the integral from a to b of f of x dx. Let's take a look at this pictorially and see what's going on here. Let's say I have some function f, and it looks maybe like this. Whoop-de-whoop. Here's my particular interval, a to b. Here's b, here's a. Great. And I want to know the area under this curve. Okay, well, it's something kind of weird, right? It's got some weird stuff going on. Well, this theorem tells me this shape is hideous. It's awful. There's some value c somewhere in this interval. Maybe it's right here. Such that if I look at f of c, it's going to represent the average value of f, which means that if I drew a straight line, horizontal line, through that point and found the area of this blue rectangle, it would be exactly the same as the area of this ugly, hideous thing. These have the same areas. And this is really, really, really nice, because what it does for us is it takes something that, again, looks kind of ugly and we're not sure how to deal with, turns it into something so unbelievably nice that we definitely know how to deal with, and it's great. Just like with the mean value theorem for derivatives, the mean value theorem for integrals only works if f is integrable everywhere. If it's not, then it's going to be a problem. We saw that with derivatives, if your function wasn't continuous somewhere, it was a huge problem, right? So again, something to bear in mind, that the conditions for this theorem are important. F has to be integrable everywhere. And again, eventually we'll be able to find this C and it'll be great, but for now it's just like, oh, does this C exist? Is there some C somewhere that has to have this property? So that's where I'm going to leave off for today. Hopefully this wasn't too much information for you, and we'll work through some good problems in class.